Hello friends, I am present here today again to discuss an important topic, and that topic is resonance scattering. I will start from resonance scattering, that is the optical scattering, and then nuclear scattering, and I will compare, and then I will try to explain an important effect which this resonance scattering gave birth to Moss power effect. So I am going to discuss. I don't know how much I could discuss today. I may be able to discuss, but I will try at least to explain. Maybe not today complete and tomorrow. So maybe in these two lectures I will explain resonance scattering and Moss power effect. So before we discuss resonance scattering, let me explain you one important aspect of decaying states. You know decaying states? Decaying states means excited states, that is unstable state. So decaying state means a state, atomic or nuclear, decaying by emission of a photon or photon in the low energy region, and same photon is called, that is quanta of energy, as gamma ray in the nuclear region. So photon or gamma ray, decaying state, the state, grounded state, excited state of energy E. Remember, every decaying state of energy E and mean life tau. Because decaying state means unstable state. So unstable state with our lifetime, our life. So energy and every decaying state of energy E and mean life tau will have an uncertainty in energy. Uncertainty energy of state. How? From where? Decaying state, as you know from Heisenberg relation. Heisenberg's relation, quantum mechanical relation. Relations here, there are two. We have one delta x and delta px. Is of the order of h cross. There is one relation given by Heisenberg, and another relation is relation for delta E, that is energy, and delta T, time, is h cross. These are two Heisenberg's uncertainty relations. Uncertainty. What the uncertainty? These two coordinates, E and time. When you are measuring energy of any system, while measuring energy you have to spend some time. You cannot measure both the quantities same accuracy. When you are doing experiment for measurement of energy, you are taking time. And that time, how much time you will take? From starting t is equal to 0, the state is born. You can take a time in measuring the time of the state, like mean life, that the state decays. So means maximum time spent in measuring energy or maximum uncertainty in the time measurement will be the lifetime of the state itself. So, maximum delta T will be the tau, mean life. Mean life of the state. So this delta T is of the order of its mean life. It has got half life, T half, it has got mean life tau. So delta T can be maximum value, then delta E, this will be minimum, will be H cross over tau. What does it mean? The meaning of this is that every decaying state has got an uncertainty in the energy measurement or in the energy of the state. The energy of this state is not well defined. It has got certain uncertainty in the energy that this state has got. Delta T is that state is not well defined. The state has got an uncertainty of how much? Delta T of the order of H cross over tau. Every decaying state has got width or energy width. There is width in the energy. Energy is not well defined, E, but it is having a variation delta E. So delta E, how much delta E? Can we get an order of delta E? How much delta E? To get this delta E, let us take some example of some atomic cases. The atomic cases, maybe say, I take some atomic case where mean life is of the order of 10 to the power minus 8 seconds. So take atomic decaying state. Say tau of the order of 10 to the power minus 8 seconds. Say the mean life of that decaying state is say of 10 to the power minus 8 seconds. And let us take some energy. So how much energy we take? Say atomic energy, its energy of the state we take say some value. If I take energy E, say of the order of 1 electron volt. A decaying state, atomic decaying state has got energy 1 eV, its lifetime mean life is this. So how much uncertainty in the energy? How much delta E is possible? Delta E in the atomic decaying state is H cross over tau. What H cross? 1.05 into 10 to the power minus 34 joule second. And then H cross over tau. Tau means 10 to the power minus 8. Calculate this value and you will find its value is about 1.05, this minus 8, 34. So how much you will have? 26, 10 to the power minus 26. This is joules. You convert this into EV. The delta E in the energy electron volt unit, if you convert, divide by 1.6 to the power minus 19, you will get its value as equal to 10 raised to the power minus 7 electron volt. What does it mean? An atomic decaying state of energy 1 electron volt has got an energy uncertainty of 10 to the power minus 7 electron volt. It is very, very small, almost negligible, very, very small. Okay? This is the energy uncertainty in the decaying state for atomic case. We take now some nuclear state. Yes, we have calculated the delta E in the case of atomic case as 10 to the power minus 7, 10 to the power minus 10 to the power minus 7 eV. In the nuclear case, say lifetime is of the order of 10 to the power minus 10 seconds. Then delta E will be equal to h cross over tau. So h cross is 1.05 into 10 to the power minus 34 and tau is 10 to the power minus 10. And you calculate this value and convert into the what to say energy of the EV, etc. This will be equal to 10 to the power minus 5 electron volt. So you see, atomic cases energy bits a typical case is order of 10 to the power minus 7 electron volt. Nuclear cases the energy bit will be right by delta E. Here delta E is of the order of 10 to the power minus 5 eV. For typical lifetime 10 to the power minus 10. In fact, if lifetime is more, then it will be less. But this shows that nuclear cases the width is more that the decaying state has a larger uncertainty as a lifetime in the cases 10 to the power minus 8. Yes, this was 10 to the power minus 7 in the atomic cases and here 10 to the power minus 4. So you can compare that atomic cases much sharper energy because lifetimes. So this is an important fact. We must remember in our mind that all decaying states they have got an energy width. I have taken a fictitious example for atomic cases. This is of the order of 10 to the power minus 7 eV for nuclear cases. For typical case of 10 to the power minus 10 seconds between life 10 to the power minus 5 eV. Good. So remember the result because we will use. Now I discuss another important aspect. What is that important aspect? I discuss another important and recoil loss of energy. What is the recoil loss? Whenever there is emission of a radiation, what happens? The residual system may be atom in the atomic case or may be nuclear in the nuclear case. It will recoil. So the emitted radiation will give some momentum to the recoiling system and hence there will be some energy loss. So I take example, say this is some system, recoiling system, it is emitting a radiation. So a radiation is being emitted from this and this has got, this is a photon. Photon of say energy E gamma or gamma ray, you can say photon or gamma ray. Same thing, energy quanta, E gamma and momentum P gamma. So what we have? This is emitted in this direction, this will give a backward recoil here to the nucleus or atom, whatever. In the atomic case, the whole atom will recoil. In the nuclear case, the nuclear excitation, the nucleus will recoil. So the recoil energy, the recoil loss, you can get that here we have ER is the recoil energy and PR is the recoil moment. Recoil energy and momentum. These are the energy and momentum of emitted radiation. So what will happen? This system is recoiling. So what momentum should be conserved? Linear momentum conservation. So what we get from linear momentum conservation? The momentum of this gamma, the momentum of this must be equal. So we have PR is equal to P gamma. Just opposite. Fine. So what? What the energy of recoil? Energy of recoil, say ER is equal to PR, that is recoil momentum, PR square over 2m. M is the recoiling mass. Simple, classical, simple, non-relativistic expressions, low energies. So M is the recoiling mass. M is the recoiling mass. And PR is equal to P gamma. So ER is nothing else but P gamma square over 2m. P gamma square over 2m. Okay, what is P gamma? Momentum of photon, momentum of gamma. So P, this is how much? P gamma. P gamma is equal to E gamma over C. If E gamma is the energy, C is the light velocity. So P gamma, we can write ER, recoil loss, ER is equal to P gamma square, means E gamma square over 2m C square. What will it mean? When a radiation is emitted in forward direction, it will give a recoil to the backward direction, recoil to system, remaining system, a residual system. What is that? Atom in the case of atomic de-excitation and nucleus in the case of nuclear de-excitation. So this is recoiling system. It means some energy is taken by the recoiling system. So whatever the energy of excited state, gamma ray will not have energy equal to that state. Why? Because gamma ray, E gamma, will be equal to E naught minus ER. Because ER is taken by the recoiling system. E naught was the, suppose E naught was the energy of that state. This is E naught. And this is the ground state. So radiation going out means this has got say delta E. And gamma ray emitted here, it is not of E naught, But this gamma ray has got energy slightly less than this gamma ray has E naught minus E R. So this gamma ray energy is E gamma. Is not equal to E naught. This is the E naught. Gamma ray has got slightly less energy. And what is the value of ER? We will calculate. So this is the recoil loss in energy when radiation is emitted. Recoil loss when emission of takes place. Well, what this value we will calculate. Now suppose this gamma ray, remember this recoil loss, that is ER is equal to E gamma square over 2m3 square. Now remember that this gamma ray or photon emitted from a decaying state is moving state inside the crystal, inside the material. So this gamma ray emitted now it is moving and it gets a system here atom or a nucleus sitting here. It gives the energy. This has got how much energy? E gamma equal to this value. This is ER. So E gamma, E naught minus ER. And this system has got energy E naught. Remember, if this energy is equal to E naught, this nucleus or atom will get excited and it will go here. If energy input is E naught. But input is how much? Less than E naught. How much? E naught minus ER. So this gamma ray falls short. How much? ER. This gamma ray cannot excite the nucleon or electron to this level because its energy is shorter by some value and that is ER. So this ER and hence this cannot. If gamma ray energy is such that E gamma is equal to E naught minus ER, such that it is much below the excitation energy. The system cannot be excited. The absorption of gamma ray is not possible by this is called, what this process is called, resonance absorption of gamma ray, because there is a resonance in the two energy. Means this energy of gamma ray and this energy must be resonating. But not resonating, it will not excite. It is not possible, absorption of gamma ray is not possible. That is called resonant absorption. But remember that this has got energy bits also. Suppose this energy bit is delta E. And I say that if delta E is smaller or much smaller than ER. What does it mean? That is, if the recoil loss in energy of emitter radiation is recoil loss is much larger than energy width of the state. The resonance absorption, this is also called resonance scattering of gamma ray. The resonance absorption will not take place if this is the condition. Otherwise, if this is larger, this is small. If delta E is much larger than ER, this will take place. Resonance will take place. But now we see this is not the case. What is the case? Actual case. What is the actual case? Actual case is when gamma ray is emitted here, this gamma ray emitted here, due to recoil loss, gamma ray energy is E0 minus ER, and this gamma ray is now going again here. And remember, delta E. This gamma ray will strike this atom or nucleus. At the time of emission it was recoiling. Now at the time of absorption also it will recoil, the atom or the nucleus. So when gamma ray strikes this system, atom or nucleus, here also there will be recoil loss of nearly same amount. Means here the mass is same because it is the same system, same crystal. In this material, gamma ray is coming out and then being absorbed resonantly. So this gamma ray here again will have, at the time of absorption, at the time of gamma ray, the system, what the system? Atom or nucleus. When at the time of absorption of gamma ray, the system will again recoil and there will be again recoil loss in energy of gamma. This gamma strikes here, this recoils and gamma has to give a momentum to the recoiling system, so again energy loss. So same here. So what will happen? The total recoil loss in the energy of gamma ray is twice of ER. ER at the time of emission and ER at the time of absorption. So total recoil loss in the radiation energy becomes twice ER. And twice ER means, if I write this by say delta ER is equal to twice ER is equal to E gamma square twice E gamma square over 2 to cancel, so E gamma square over MC square. So delta ER is E gamma square over MC square. Means recoil energy loss total while emission and absorption takes place. This is equal to E gamma square over MC square. Now let us calculate this value, atomic case. In the case of an atom, say I calculate this value for certain fictitious value of radiation. Say E gamma photon energy is say 1 electron volt. Recoiling mass is say 50, means atomic weight A is equal to 50. So that will take mass of nearly 50 protons. Neutron proton mass nearly takes same. So 50 times mass of proton. A is equal to, so that is M. This is in fact here M. So we take here M as 50 times mass of proton, because we assume that there are 50 protons or neutrons total, so we take mass of proton, neutron nearly equal, so 50 times the mass of it. So we calculate this. The E gamma 1 electron volt, so what is delta ER? Delta ER is a case of atom, that is E gamma square. What is E gamma? 1 electron volt. 1 electron volt converted into joules. So this is say 1.6 into 10 to the power minus 19 square. That is E gamma square. M is 50 times mass of proton. So 50 into mass of proton, say 1.66 into 10 to the power minus 27 kilogram. And C square, so into C square means 3 into 10 to the power 8 whole square. So what we get from this? We get from this, you calculate this in the proper unit, delta ER is equal to, if you calculate this value, the value will be 2.1 nearly, 2.1 into 10 to the power minus 11 electron volt. What does it mean? In the atomic case, if a photon is emitted, if a photon of 1 electron volt is emitted, and it is resonantly absorbed by the system, by the emitting state, what happens? There is total energy loss due to recoil, emission and the absorption time. That is this order. What was the energy width? Energy width was delta E. I write this by say some symbol, say gamma. That is energy width of decaying state. and this is this for atom. This gamma was of the order of 10 to the power minus 7 electron volt. And delta ER is equal to nearly 2.1 into 10 to the power minus 11 electron volt. So what do you infer from this? What do you get from this? You get from this the total recoil loss in the energy is much smaller than the decaying width of the decaying state. Means this state has got, say, this much width. Suppose this is E naught, suppose. So this is a gamma of, or half you can take because you divide plus minus. E naught, then this energy loss, this is the 10 to the power minus 7. Gamma energy is less by 10 to the power minus 11, much smaller. So this gamma can raise this system atom or electron inside, because this gamma energy is now here, how much? E gamma minus 2 into 10 to the power minus 11. While we have here this energy, how much? E naught minus say 10 to the power minus 7. So this energy goes inside, means the width is much larger than the recoil loss. That is, the width is much larger, that is, gamma is much larger than delta ER. In the atomic cases, so what we get? In the atomic cases, this is much larger, means this is much smaller. What is possible? Therefore, resonance scattering of a photon in atomic cases is frequently observed, very easily. Readily observed, very easily. So resonance absorption of radiation phenomena takes place in the case of atomic excitation very easily. We observe this since last several years we have been observing. So what is so much important? Well, atomic cases we observe. People then try to see the resonance scattering in the case of nucleus. When we discussed the introduction of gamma ray in the first lecture, I told you that three important interactions of gamma ray are photoelectric, Compton effect and propulsion. There are many others, very, very small, Dalberg scattering, Compton scattering, etc. In this there is one scattering which is nuclear resonance scattering. That I told you that I will discuss it separately. Because this is an important topic, this gave birth to an important effect known as most power effect. So I am discussing that separately. This is atomic cases, this is very easily observed. But nuclear case, we have seen, what we have seen earlier, that H cross over tau, delta E, of which we have taken as the capital gamma, is equal to H cross over tau. This we got how much? For a fictitious case, 10 to the power minus 5 eV. In a fictitious nuclear case, of 10 to the power minus 10 half-life. at 10 to the power minus 5 eV. And recoil loss, total recoil loss. Total recoil loss, which we have calculated, how much? That is E delta ER equal to E gamma square over MC square. So nuclear case delta ER, you calculate how much. E gamma we took a fictitious value, how much? E gamma we have taken for the calculations, how much? Fictitious value, take any value, energy of the nuclear decay. The level of energy we take 2 ER we have calculated atomic cases, it was 10 to the power minus 11. But for nuclear case, I have to take some example. What example I should take? For the nuclear case, say, suppose we take, again say A is equal to 50. That is a nucleus of mass 50 is decaying and it is emitting a radiation of the energy E gamma is equal to say 100 keV. A nucleus of mass 50 decaying by emission of 100 keV gamma ray, its mean life is 10 to the power minus 10. We have calculated already that this is equal to 10 to the power minus 5. What is delta ER? Well, delta ER will be, you calculate, will be how much? E gamma square over MC square. So this is how much? 100 keV, 100 into 10 to the power 3 keV, so 10 to the power 3. And unit convert 1.6 into 10 to the power minus 19. This whole is square, E gamma square, over M. M is 50 times mass of proton, 1.66 into 10 to the power minus 27. And this is 3 into 10 to the power 8 square. So find out this value. Calculate, take a calculator and find out the value. Delta ER. If you calculate this value here, in this case, its value is, I have the, 0.21 electron volt. You find out the value. What does it mean? In the nuclear case, delta ER much larger than gamma, capital gamma, the width. Energy loss of gamma ray while emitting and absorption is much large. Means if this was the state, this was the width, gamma ray energy loss is such that ER, total twice ER or delta ER, the ER is 0.21 electron volt. So this is much larger because this is 10 to the power minus 5. Very small. This is 0.21. So gamma ray means in the nuclear case delta ER. So what happens? Gamma ray energy is much smaller than E naught. Because gamma ray energy is how much? E naught minus delta ER. So that is gamma ray energy is how much? E gamma is E naught minus delta ER. So delta ER is very large in the nuclear case. So what happens? In the nuclear case, in the nuclear case, nuclear resonance, in the nuclear case, resonance scattering of gamma ray is very difficult, almost not possible. So for several years, people were trying to get nuclear resonance scattering phenomena. What we have to do? We have to compensate this delta ER to have the nuclear resonance scattering to observe nuclear resonance absorption of gamma ray. We have to compensate ER equal to E gamma square over MC square. We have to compensate. We have to supply this thing so that gamma ray energy approaches within the width of the radiation, width of the decaying state. So we have to compensate this. We have to design some methods. One of the methods can be to overcome ER. I give you here the energy line. This was the energy of the state E naught here. So we want to excite this. Due to energy, I will show both sides energy loss. Say this is the energy E naught minus this side RT plus scale is ER. This is the energy level E naught minus ER. What we do? Energy less. I have shown this. Okay, I also show the same value. Or I show that this is ER. This is ER. So this gamma ray, in fact, I show this energy less by this. So this is energy less. Means at the time of, if this is the gamma ray energy, then at the time of emission it becomes E naught. Then at the time of absorption this becomes E naught minus ER. So total loss is twice ER. I have to compensate this. Means I have to do something so that These are so many cases, gamma ray of energy of different energy coming out. Some gamma ray will have energy equal to E naught. That number will be very small, overlapping this here. Energy, if I do something, I pump energy so that this energy becomes nearly this. Then from here, so much loss, I have to supply something, some energy, so that this radiation gets the energy more, so it comes here. So I am drawing a curve like this. You see, there is one phenomenon you might have heard of, we have read many times. One is called Doppler shift, Doppler broadening. What is Doppler broadening? A moving source, a moving observer, its frequency changes with the velocity, and I have say expression of Doppler broadening. I write by symbol gamma G. This is given by, you can see the any book of optics or also sound, that E, if E is the energy radiated by the source in moving source and moving with the velocity v, E v over c is the broadening, Doppler broadening in the energy. In the frequency broadening, the energy broadening. So this is the energy broadening more due to velocity v. Means velocity v means moving source. A source is moving with velocity v, moving source. So this is the Doppler broadening. If somehow you can compensate, you can give this value equal to this value, that is the delta ER. Suppose this is equal to delta ER. Then what will happen? The recoil, total recoil loss at the time of emission, at the time of absorption is compensated by a moving source. So it is possible either you have a moving radiation in nuclear reactions, means moving radiation, means in a nuclear reaction a particle is moving because energy is pumped by the projectile. So it is moving with certain velocity, and that is emitting gamma ray. So gamma ray emitted by a moving particle, moving the nucleon, this will compensate the energy loss, recoil loss. So moving radiation, nuclear reaction, you can design some experiment where you have produced some activity, and that particle, the emitted particle moving certain velocity, and that is giving gamma ray, emitting gamma ray, a nucleon de-excited. So that gamma ray will not have recoil loss. Which gamma ray? A gamma ray coming in the nuclear reaction, maybe recoil loss is compensated by moving emitter. Which emitter? A system is emitting gamma ray. So that is moving. So that if the velocity of motion is such that, and gamma energy, that it compensates the total recoil loss. It is possible that recoil loss may be compensated. What else is possible? Another thing is possible that this EV over C can be compensated by, one method is, you say that you have kinetic theory of gases where you have uh, you have energy. From that you have in a week you can calculate from the, or energy can be calculated. You can write at certain temperature. We can write that Doppler broadening, I am writing this as broadening only. Here also this is compensated by moving emitter, and here this is equal to E V over C, and this I write as V is the from kinetic theory of gases, and I write this E as the energy of the state E naught suppose, and V is equal to from kinetic theory of gases 2 kT over m. Velocity V at temperature T. T temperature, that is 273 plus room temperature theta, whatever. So absolute T temperature. So from this, it means you can compensate this. To compensate the recoil loss means you have to provide this much energy so that you get this equal to recoil loss. Then this is the temperature. So you have to heat the source which is emitting radiation to certain temperature T, so that this T you can calculate to get this much, how much velocity. This can be calculated scientifically. You can get the value of, say, how much should be temperature for this. That can be calculated. Another method of compensating, to compensate the recoil loss, EV over C, suppose this EV over C is equal to E gamma square over MC square. To compensate this, to provide certain velocity V, what you do? You move the source by a motor. Here it was, source was moving by nuclear reaction. Here you have heating by certain temperature, giving energy from kinetic theory. Here you move the source by a electric motor and find out the velocity. What should be velocity to move the, you can find out that this for E gamma equal to 100 keV, same mass 50, etc. You can find out the velocity V, that so that it compensates E gamma, and this is also, so E means same thing, E gamma. So this E gamma one cancel. You can find out V is equal to 1C also cancel, E gamma over MC. V is equal to E gamma over MC, and find out this value. For E gamma is 100 keV, you find out V, put the mass, say 50 mass, A is equal to 50. You find out V will be of the order of 5.4 into 10 to the power 2 meters per second. That if you move your source by electric motor, by this velocity, you can compensate the total recoil loss in the energy of gamma ray, E gamma square over MC square, at the time of emission, at the time of absorption, by moving the source by the velocity v, and we find that the velocity v for a fictitious case of 100 kV radiation from a 50 mass system, the velocity comes out to be 5.4 10 power 2 meters per second. So you have to move your source by this velocity. then that gamma ray can be resonantly absorbed. So these are the methods for observing the recoil loss, nuclear resonance scattering. In the next lecture, I will explain you that what Mossbauer did. Mossbauer did for the nuclear resonance scattering, how he achieved. Remember, Mossbauer was a PhD research scholar in 1959 probably, and he is a German. His scientist, his boss, his supervisor gave some problem. He was not interested in that problem. He was independently thinking on this problem of nuclear resonance scattering. And he typically thought something, and he gave very simple explanation to get resonance scattering. And on that topic, this was additional to PhD program. He was doing PhD in 1959, and he was thinking on this problem at the same time without the consent of his advisor. And he published the paper on this. He got in 1962 Nobel Prize on this topic. This was so much burning and so important. So in the next lecture, I will try to explain some easier method as taught by Mossbauer, and then I will try to explain. Mossbauer effect has got now tremendous application. There are thick volumes of books written on this. It has applications in the chemistry, it has applications in the astronomy, astrology, and etc., in the moving of the galaxy, etc. That is red and the blue expansion of galaxy. And it has, we can get the nuclear lifetime also. So many applications of Mossbauer effect. So next lecture, I will try to explain how Mossbauer thought on this simple thing and how Mossbauer gave a simple method to see the nuclear resonance scattering, which was very difficult task in those days. So thank you very much for listening my lecture.